Okay, still having microphone problems? So you won't hear Mrs. G's voice here. I'm voicing over for her. Classifying reactions. All right. The reason why we classify reactions in chemistry is because when we classify reactions, it helps us to be able to predict the products so that we know what's going to happen when we actually combine two things together. There are 5 basic types of chemical reactions that we talk about in regular chemistry. There's a combustion reaction where things burn. There's a synthesis reaction where things are made. There are decomposition reactions where things are broken down. There are single displacement reactions, which usually involve salts, and one element, is going to replace a single element in the salt to make a different salt. And there are double displacement reactions where we start out with 2 salts, and the ions of the salts actually switch places. Okay, it turns out that these 5 basic types aren't the limit of what's possible for chemical reactions, but talking about that is beyond the scope of this unit, so we're not going to talk about that. Just warning you about that because at some points in chemistry you're going to find some difficulty pigeonholing a reaction into one of these 5 categories. Combustion reactions, let's get things started here. Combustion reactions are always going to have a carbon compound as a reactant. This carbon compound can be the form of gasoline, coal, starches, alcohol, sugars, cellulose, oil, etc. But it's always going to be a hydrocarbon, meaning it's a compound with carbon and hydrogen in it. And I'm going to actually write that word down. So it's going to have a certain amount of carbon and a certain amount of hydrogen in it. Okay. Notice the 2 variables, x and y, they're not necessarily the same amount of carbon and hydrogen. The other thing that you need is energy in a chemical reaction, so we're going to be using the delta symbol. And also you need to have some oxygen gas, free oxygen gas. Notice, guys, it's not just in a compound, it is oxygen gas. The products always wind up being water, carbon dioxide, and energy. Okay, here's an example. Notice, okay, I'm going to change the hydrocarbon so that it's CXHY. But notice here, guys, it's the same basic idea. You got a hydrocarbon, you've got oxygen gas, you've got delta, meaning that there's energy being used, water, carbon dioxide, and energy are being created. So this is propane, C3H8. And this is just like your gas grill at home if you've got one at home. I know I have one at home. Your propane needs oxygen in order to burn. It needs a tiny little spark. I usually light a match to light my grill. Some people have those nice piezoelectric igniters. You just push a button. It does produce carbon dioxide. It produces water, vapor water, because it's so hot. And it produces a heck of a lot of energy so you can cook, and also that makes the water a vapor. So you don't see water dripping off of your grill. You see the steam coming off the top. All right, a synthesis reaction. Synthesis is coming from the Greek, meaning to be put together. 2 or more formulas are going to be combined to form a compound in this kind of a reaction. Example, A plus P yields AB. So you got elemental A and elemental B that make a compound, AB. Elemental sodium and elemental chlorine can be combined together to form table salt. Decomposition is the exact opposite of synthesis. Usually compounds become elements. So a compound AB would be decomposed, would react, and form elements A and B. Usually this requires a little bit of energy to get it to happen. Water can be decomposed. We decomposed water using the Hoffman apparatus, and you wind up getting hydrogen elemental and oxygen elemental, or as Miss G likes to call them, oxygen gas and hydrogen gas. The airbags in your car, if you've ever had the airbags go off, you've got a compound that's in the steering column. The compound is sodium azide, or let's see, we would name that sodium tetranitride, although the common name is sodium azide. Basically what happens is you get a spark generated by your bumper getting hit, Your bumper's wired up to the steering column, and you get a little bit of a spark that goes up to the sodium azide. That spark starts the decomposition reaction, which is extremely fast, and it forms elemental sodium and nitrogen gas. The nitrogen gas is what's actually filling up your airbag. If you've ever actually gotten into an accident and you've touched the airbag shortly after, you realize that the airbag is actually pretty hot because this generates a lot of energy, this decomposition reaction. All right, sometimes we have compounds that have 3 or more elements, and usually those things break down into compounds. I'm just telling you that because you want to be able to recognize a decomposition reaction, not because we want you guys to be able to predict those products. So, for instance, a compound made of A, B, and C might break down into AC and BC. 2 more kinds of reactions. Single displacement is one of them. Single displacement, an element replaces another element in a compound. The rule for this is that like charges always exchange places. So you're going to have to look at the periodic table and see what charge the element usually becomes, and then look at which of the 2 things in the compound has a similar charge. So cations are always going to replace cations, and anions are always going to replace anions. My example here, my simple example, A and element A and compound BC form compound AC and element B. Notice, guys, that A and B are expected to both be cations, positive ions. I can tell that because B was listed first, and they wound up switching places. Here, we've got an example, aluminum and copper chloride. I can tell right off the top that aluminum and copper are my metals, so they're going to wind up switching places when we get to the products side. So instead of having copper chloride, I'm now going to have aluminum chloride, and what do you know? There we are. Notice that the subscripts on this had to change because aluminum is a +3 element and chlorine is a 1-, so we actually needed 3 chlorines to make this a stable compound. And the copper winds up being by itself, just like aluminum was at the beginning. Here we've got a slightly different example, magnesium bromide and chlorine gas. Chlorine is an anion and bromine is an anion, so I'm expecting those 2 to actually swap places on this example. So I'm going to be expecting to get magnesium chloride and bromine gas. Again, we're checking the charges, we're writing things as diatomics if we need them when they're elemental, if they need to be. Notice copper was not diatomic, so we listed it as Cu. Bromine is a diatomic, so we listed it as Br2. Here, double displacement, one more type. So double displacement has 2 compounds as reactants. That's the difference between single displacement and double displacement, is that single displacement has an element in a compound, double displacement has 2 compounds. Okay. We're still dealing with the same sort of rules. Like charges are still. An interesting note is that double displacement reactions always result in a solid, a gas, or a molecule forming. A molecule is a covalent compound, remember. So 2 nonmetals. So that's one way to actually check to see if it actually is a double displacement. So here we have AB and YZ, 2 compounds. I can see that since A and Y were both written first, that they're going to be cations, so they're just going to swap places with each other. Okay, so that means that A is going to wind up with Z, and B is going to wind up with Y. Notice when we rewrite them, though, we make sure that the cations are listed first, positive for A and positive for Y, so both of them got written first. All right. Here is an actual example. Potassium iodide and lead nitrate are going to get combined together here. Notice potassium is a positive and lead is a positive. Okay, as a matter of fact, lead happens to be +2 and potassium has to be +1. Okay, so when they switch places, I'm going to get potassium nitrates, which is KNO3 here. 1 and 1, so I will only need 1 of each. And then lead is lead-2 and iodine. So we've got lead, which is a 2+ charge, and iodine, which is a 1-, so we needed 2 of the iodines. All right. Another example, silver nitrate and aluminum chloride can combine, and they're going to change places also. Silver and aluminum are going to change places, so we're going to get silver chloride and aluminum nitrate. Okay, here's the homework. So classify the following types of reactions. Do it on a clean sheet of paper. Write down chemical reaction homework number 3 at the top. Okay.